All right. Um, I'll go ahead and get started then. So, hi everybody. Today I'm going to be doing a presentation on the topic of albedo and its implications for a warming planet. So, before I get started, I'd like to just thank you guys for tuning in to this recording or watching this lesson. And COVID-19 has certainly presented many challenges for education and as far as reaching the students goes. So we here at the Wisconsin Energy Institute are incredibly grateful to be able to continue to reach students like you guys with science topics and to foster your curiosity, even if it has to be virtual like this. We are very grateful for the opportunities that we have to do so. So also, my name is Alana Rapp, and I'm a senior at UW-Madison studying environmental science and German. And I've been working at the Wisconsin Energy Institute for the past 2 years, alongside Allison Bender and Scott Williams in the Department of Education and Outreach. So we do programs like this, but also a variety of other things. So we'll get started then. So the Wisconsin Energy Institute is what I'm here representing today. And the Institute is a home for cross-disciplinary energy research at UW-Madison. We support over 160 researchers studying things from microgrids to biofuels, and we also support the next generation of energy experts via certificate programs at UW-Madison. So if you're thinking about college and you're interested in energy, be sure to check those out. We also do a variety of public outreach and educational programs such as this one, or these virtual lessons. We'd also like to acknowledge that the land that the Wisconsin Energy Institute occupies is the ancestral home of the Ho-Chunk Nation, who call this land Dejop. The Ho-Chunk Nation and the other 11 First Nation residing in the boundaries of present-day Wisconsin remain vibrant and strong. We would like to recognize and respect the inherent sovereignty of the 12 First Nations that reside in the boundaries of the state of Wisconsin, and also acknowledge that the tribes are doing some of the most important and leading work in transitioning to clean energy systems. So the Wisconsin Energy Institute is also partnered with the Great Lakes BioEnergy Research Center, which has its home and has scientists working both at UW, but also at a few other different universities across the US. Over 400 scientists and staff from these multiple universities are working to find a way to make fuels and products out of sustainably grown plants like switchgrass, poplar trees, and mixed prairie. That's the work that's being done at the Great Lakes BioEnergy Research Center. All right, so a quick overview of what we'll be covering today in this lesson. We'll start with a definition of what albedo is and an explanation. Then we'll go on to discuss the Earth's energy budget, how albedo functions on Earth, as well as the relationship between albedo and temperature. We'll then discuss the exploration of scientific phenomena via experiments, including a case study and some predictions of our own. We'll then discuss the effect of albedo on climate with an overview of this process and a discussion of specifically how albedo affects climate change. And finally, we'll wrap up with some research that's being done at the GLBRC, an overview of this and the implications of this research. So I wanted to mention at the beginning too, feel free, as this is not an in-person lecture, but rather recorded, to pause the video whenever I ask any questions. I'll be asking some throughout the lesson in order just to gauge your guys' sort of understanding, and also for you to make some predictions as to what we'll be talking about next after we've talked about a little bit of something. So it's a good way to kind of engage in the lesson as we're going on. So feel free to just pause the video at those points, and I'll mention that as well, so that you can either, if you're on your own, just think of it in your head, you can say it out loud, you could write it down on a piece of paper, or if you're with some classmates or siblings or other people, feel free to discuss amongst each other your ideas to those questions. So what is albedo? So albedo is a measure of reflectivity of a surface. So we're most often interested in this phenomenon in terms of solar energy, so the sun's rays, how much of these rays are absorbed by a given surface and how much are reflected. So albedo is measured on a scale from 0 to 1. effectively representing the percentage of solar radiation which is reflected from the Earth's surfaces. So 0% would mean 0% of the sun rays are reflected, all of them are absorbed, and 1 would correlate to 100% are reflected and none are absorbed. So my first question to you guys would be, what do you think make up the bookends of this scale? What do you think in terms of surfaces or colors, or what do you think are going to be having an albedo of 0 and an albedo of 1? Feel free to pause the video here. So if you were thinking something along the lines of that black would be having an albedo of 0, a black surface, and that white, or in perfect terms, a mirror, would be having a reflectivity of 1 or 100%, then that would be totally correct. And there are other answers too, like maybe you guys said shiny objects are likely to reflect more than rougher objects. That is also completely true. But in terms of kind of making up 0 and 1 of that scale as definitively as we can tell, black surface is a 0, an albedo of 0, and a white surface or a mirror ideally has an albedo of 1, meaning it reflects all of the incoming light. So albedo is also related to temperature in that a greater absorption of sunlight results in a greater warming of an Earth's surface. So a surface that has a lower albedo and is absorbing more of the incoming light will be heated up by that process because they are absorbing that light, which is in the form of energy. You can maybe think of some examples in your life where you've noticed this phenomenon before. Some times where you've seen the correlation between color and temperature, or surface, qualities and temperature. Can you guys think of any examples? Feel free to pause the video here and take note of those. So the ones that I thought of that came to mind most immediately was, for example, in the summer, if you were to touch a street or a surface that's covered in asphalt, it can oftentimes be really, really hot. In comparison to maybe like a cement sidewalk might be not quite as warm, as it is made of like a lighter gray color, so it reflects some more of that incoming sunlight. Or, for example, the clothes that one might wear in the summer, if you wear lighter colored clothes, it can keep you cooler because they're reflecting more of the incoming light. Or even a car, for example, say that your parents drive a car that has a very dark color or a lighter color. You might notice that that dark color, if you get into it in the summer, it's particularly heated up. And that's because it's absorbing a lot of the incoming sun rays. So it's warming. So we've established that albedo is a measurement of the reflectivity of solar radiation by Earth's surfaces. So now let's talk a little bit about the dynamics of this system, which we label as the Earth's energy budget. So solar energy reaches the Earth in the form of electromagnetic waves. That's kind of what this image here is showing. And then a portion of these incoming rays are absorbed by the Earth's surfaces, and a portion are reflected back out into the atmosphere, about 70 and 30% respectively. So about 70% of the incoming rays are absorbed and 30 are reflected. There are lots of intermediate stages in the system. For example, some incoming rays are reflected off of clouds and vapor that are in the atmosphere before they reach Earth. Some are absorbed by the Earth, but then re-emitted as heat. That's what this orange arrow is here. But what we are most interested in is the reflection of the sun's rays by the Earth's surfaces due to the albedo of these various surfaces. So that can be seen in this incoming yellow ray. There's a good portion that are absorbed here. Like I said, there's some intermediate stages. These rays are reflected off of the clouds before they even reach the Earth's surface. And then this is the amount of reflected rays coming off of the Earth's surfaces due to albedo. So about 70% here and 30% here. So understanding albedo is crucial to understanding the Earth's energy fluxes. Scientists monitor changes in the Earth's energy budget, which can be loosely defined as how much of the sun's energy is being absorbed or reflected by the Earth, as an important indicator and tool in understanding how and why global temperatures are rising. So these changes include changes in albedo. Albedo varies naturally throughout the year, which we will talk about a bit more later in the lesson as to why that is. And then also on grander timescales, think ice ages, for example. If the Earth is a big snowball, it's bound to have a different albedo, different amount of reflectivity than what we have now. However, human changes to the Earth have also caused significant shifts in albedo and may continue to do so, which is a phenomenon we're very interested in understanding better. So I'm going to present you guys with this question now and just have you be thinking about it as I discuss the next slide, and then we'll come back to it after that again. So the question is, what are some of these human activities that could change the albedo of Earth's surfaces? So feel free to just think of those as we discuss the next page, and then I'll pause the video, or you guys can pause it again to think more if you need. So it's clear that human-caused activities or human-ran activities have changed the albedo of Earth's surfaces. To better understand how these changes affect the albedo, let's discuss what factors in the first place influence albedo and how it functions on Earth. So this is a really helpful image here. You can see various different landscapes on Earth that are commonly found and their corresponding albedos. So again, we're given the albedos in a percentage form, which means the percentage of the incoming sunlight that is reflected off of that given surface. So here, fresh snow has a very high albedo because it's reflecting a lot of the light that strikes it, versus forest is a very dark colored, more textured environment, and it absorbs a lot of the incoming sunlight rays and only reflects 10 to 20 or so. Water bodies also, here it gives a range from 10 to 60, but it generally falls more on the lower end of this range. So water bodies are often quite dark and absorb a lot of the incoming sun rays and reflect very little. And then the same is true of asphalt. And then there's some higher albedos for lighter colored brick or stone, for grass. Right, exactly. And then over on this side, we see a little diagram that kind of represents or shows us how albedo functions as well. So here are two different planets, and this is the sun. And we can tell that this planet is going to be hotter than this one because it is much closer to the sun, so it receives those incoming rays at a higher intensity. However, these two planets are the same distance from the sun, so they receive the sunlight at the same intensity. However, this one is a white color and this one is a dark gray color. And therefore this planet will be hotter because that color is absorbing more of the incoming rays and reflecting less than the white. And then here is a little diagram that kind of gets at the greenhouse gas effect, which we'll discuss a little bit more later. But that's this purple ring is this sort of insulative layer, which again causes heating in that it traps the incoming sun rays close to that planet and warms it. So what is a factor or characteristic of a surface which we have already discussed that has a major effect on albedo? Feel free to pause the video here. So the main one that we've discussed thus far, though we have discussed a few, is color, right? And that's just an easy one to keep in mind to kind of categorize or explain why these different surfaces exhibit the albedos that they do. So, you know, dark green forest, dark brown, dark asphalt, those all have lower albedos, meaning they absorb more light and reflect less, versus the prairies or lighter colored or snow, for example, surfaces, which will be reflecting a lot more of the incoming lights or incoming rays. However, this is not the only thing that affects albedo. There's also other characteristics of surfaces such as their texture that will affect albedo. For example, shinier, smoother surfaces reflect more light than rougher surfaces. So it is a quite complex value, the albedo of a surface, but for our purposes, we'll be looking mainly at the color of the surfaces and how that affects them. So let's come back to that question that I asked 2 slides ago. What are some human activities which change the albedo of Earth's surfaces? Feel free to pause the video here and discuss what your ideas about this might be. So the different ideas that I came up with for this, for how, for what human activities change the albedo of Earth's surfaces were, for example, the melting of ice glaciers, Also the melting of ice in areas like tundra environments, which then exposes this very dark brown black soil underneath that certainly has a much lower albedo than the snow that used to be on top of it. Also, depletion of soil and kind of the after product of what happens to lands that are over farmed. Also sprawl of settlement across an area. For example, here we can see that there's a lot of dark colored streets in this town that maybe used to be a grassland or something. So that'll change the albedo as well. Also the colors of the rooftops and such. Agriculture changes the albedo of land. If this was previously forest or prairie, it's different now with the agriculture. Then also air pollution and industry and deforestation. So these are some examples of things that humans are doing that change the surfaces of the earth, which in turn change their albedo. So here is a general map of the world. My question to you guys is, what would you guys guess the different areas of the Earth's albedos to be? So for example, where are kind of the forests of the world, the deserts, ice, and you can just say higher or lower albedo. You don't need to give a number. But yeah, just pause the video here and try and identify sort of where the highest and lowest albedos of the Earth will be, what this map would look like. So in case you guys needed a bit more help with this, there's also, we can just discuss really quickly, here is a very large deserted area. Here you can see with the green near the equator, there's quite dense forests. Then we also have like the northern forests up here and in North America. Greenland is full of ice. There's also some ice in these kind of top parts near the Arctic region. Also a bit of ice at the very bottom of South America. Desert over by Australia. Yeah. Okay, so here, now let's compare your estimates with data on albedo, which has been collected by the NOAA and NASA SUMI NPP satellite. So the image represented here is from data that has been collected on the albedo of various Earth surfaces ranging mainly from 0 to 0.4 on land, reaching near 1 on ice-covered areas. So the red areas are the most reflective with high albedo, meaning they reflect a high amount of the incoming sun rays. And then blue is the most absorbent of incoming light rays and therefore has the lowest albedo. So that's the range we see here from 0 to 1. So what are your guys' initial reactions to this map? You can tell that this is just really covering the land. So unfortunately, we don't see what the ocean albedo is, but I wanted to focus first here on the land, and then the Arctic that has no data. That's why that is this beige color. But yeah, look at the rest of the map and take note or think to yourself whether this resembled kind of what your estimates were. And if not, do you find anything surprising? Are you do you feel like this makes a little bit more sense than what you had been thinking of? Or maybe you feel like you don't understand why certain areas are the colors that they are? Feel free to pause the video here. Give it some thought. So we mentioned earlier that albedo is related to temperature. And but this is not a one-to-one relationship, because it's important to say here, maybe one of the things you guys said that you found confusing would be that the albedo doesn't necessarily follow kind of temperature. So it's not like the darkest, the lowest albedos are found right at the center where the equator is, and then they get progressively lighter as they go out, thinking that, if the center has the lowest albedo, it's absorbing the most heat and is the warmest and then gets cooler as you go out. That's not necessarily the pattern that we see here. It really has more to do with the specific surfaces. Albedo is a property of a given surface that is usually pretty consistent for that surface. So, but what we can notice here is that up in those forested regions in the top of North America and along the top of Asia and Europe, as well as right around where there's very dense kind of jungle and forest along the equator here in South America and in the middle of Africa. Those are some of the darkest areas, meaning the lowest albedo. So these regions will be absorbing a lot of the incoming sunlight and reflecting very little, versus where this desert is here and a few other deserted regions we can kind of see over in Western North America, along the side of South America on the west coast, in Australia. So these are all places with somewhat higher albedos, meaning they reflect more of the incoming sunlight. Um, and you know, when you think about it, sand has a lighter color generally, and so it'll be reflecting more of that incoming sunlight. Of course, the highest albedo that we see on this map is in Greenland, which is covered by ice. So that would probably make sense too, if we think about it. So yeah, we mentioned earlier, like I said, that there is a relationship between albedo and temperature. However, in this image, it's not a perfect one-to-one correlation, as we see. However, the pattern that is maybe more important to witness is sort of the changes in albedo in relationship to temperature throughout the year. So seasonally, seasonal variations. So this image shows that pretty well. If we can look at the first and third rows, these are images of the Earth taken from outer space, simply as the Earth looks. And then rows 2 and 4 are the albedos of the various surfaces of the Earth. So feel free to pause the video here and just take some notes or talk out loud about what you are noticing. Again, here is December through February, March through May, June through August, and September through November. So throughout the course of 1 year, how do you see the albedo changing across the Earth, and in what ways? So this second image here, or this image that we're looking at here, was captured by the NASA Jet Propulsion Lab in the California Institute of Technology. And you guys may have noticed that as we look throughout the year, the albedo is generally highest on an average, as an average, in the winter months. And so a reason for this could be the accumulation of ice and snow. So if we're looking in the December through February and the March through May, we see that there's a lot more red in northern and sort of nearing central Asia. And that is probably due to the accumulation of snow and ice during these months, which have both a very high albedo, reflect a lot of the incoming sun rays, versus the summer months. It looks almost all blue or blue and green, meaning most of this land is now covered with a dark green forest and has a much lower albedo, meaning it reflects a lot less of the sunlight and absorbs a lot more. Is this sort of along the lines of what you guys noticed when you were taking note of your observations of these images? Feel free to pause the video again and kind of debrief now that we've pointed out those patterns. So albedo and temperature are clearly correlated, as we've been talking about. When a larger percentage of incoming rays are absorbed by a surface, meaning it has a lower albedo, the surface heats up. This is because the sun's rays reach the Earth as heat energy. This correlation is most visible in looking at the seasons and their relationship to albedo. So here on the right, again, are two graphs that came from a study done in or conducted by Yang-Hung Hu et al. On albedo in northern China from 1992 to 2012. It's a study that we'll be discussing more on the next slides, but I think these graphs are very indicative of the patterns that we're trying to establish here, or that we're looking at, which is that the albedo is much higher in these winter months, these first couple and these last few, and then lower during the summer on average. So this trend is explained mainly by a greater amount of ice and snow in the winter months, which have higher albedos. So the relationship between albedo and temperature has significant implications for an already warming planet. So the snapshot that we saw in the map a few slides earlier, this one, and this is sort of a snapshot in time. So we're thinking that this, I think that this map was, the data for it was gathered sometime maybe in spring. So we can see that there's already here darker albedos, so probably more trees and such growing here. This map might look a little bit different in the winter, but this is a snapshot in time of what the albedo of Earth's various surfaces look like. And although those fluctuate throughout the seasons, they kind of fluctuate in a very patterned way. But as human changes to the Earth's surfaces are changing what these surfaces look like throughout that year, these year-long patterns and seasonal variations are being skewed. So one of the good examples of this is the melting of glacial ice, which normally has a very high albedo and reflects a lot of the incoming sunlight, which then turns into dark water when it is melted, which has sort of the flip side, a very, very low albedo, meaning absorbs most of the incoming sun rays. So changes like these are causing significant changes to these patterns in albedo that have been pretty consistent for centuries now. So a great way for scientists to further explore a scientific phenomenon that they are interested in are experiments. So what is the purpose of an experiment? You can pause the video here to talk about that for a little bit. So the main purpose of experiments is to answer a question. So scientists are studying a phenomenon, they have a question about it, and then they design an experiment to be able to kind of further dive into that question and see what the answers to their questions might be. So an interesting study titled Human-Induced Changes of Surface Albedo in Northern China from 1992 to 2012 sought to answer some questions about albedo. The study analyzed the effects of different land covers in Northern China on albedo and how human changes to that land cover thereby affected or changed the albedo. So here's a map of that section that they were studying of Northern China. And a key on the side here shows the 6 different land covers that they were interested in collecting data on. So there's agriculture, forest, grassland, settlement, water, and bare area, which was defined as sort of desert or kind of barren land. So feel free to just kind of study this map for a moment if you want. You can pause the video. So now we're going to hypothesize the results of this study. So what do you guys think was the purpose of their study? We kind of just talked about it on the previous slide. And what are your estimates for how the albedos of different landscapes ranked on a scale from 0 to 1? So the purpose, feel free to pause the video. So the purpose of their study was to investigate the different albedos of these different land covers, and then to understand how they've been changing due to human activity, and therefore we can see how the albedo of the land in northern China has been changing. So the first step in this experiment was to establish the albedos of these different land covers. So I'd love for you guys to pause the video now and go ahead and try and rank these 6 different land cover types on a scale from 0 to 1, from the lowest albedo, meaning again, the least amount of sunlight reflected, most of it absorbed, to the highest albedo. So the most amount of light that is being reflected and the least that is absorbed. Go ahead and rank these 6 in order along a scale from 0 to 1. All right, so here are the results of the study. We can see that the lowest albedo, the surface that had the lowest albedo was water, then forest, then settlement, agriculture, grassland, and bare area. So that was kind of the order there. How did these results compare to your guys' estimates? Was this kind of similar to what you were thinking of? Does this sort of make sense, this pattern? Did the results of the study surprise you? So the way that we can kind of understand these results is water has a very low albedo because of its dark color, and it absorbs a lot of the incoming sunlight and reflects very few rays. Um, Forest is also sort of a dark green. Settlement tends to have darker colors, roads, maybe darker building materials. Then agriculture is a bit higher of an albedo, but still lower than grass, which is like natural grassland, which is often the landscape or the land cover that is transformed into agriculture when agricultural fields are established. So you're taking a land that previously had a higher albedo and changing it to one with a lower albedo. And then bare area has the highest albedo of all of them. So yeah, did these results surprise you? Is this kind of what you guys were anticipating? So there are a few very important implications of the results of this study to kind of take away. If we can better understand the correlation between different landscapes and their albedo and our effect on these landscapes, what would this allow us to do? What do you guys think this would allow us to do? How could we maybe do things better if we understand this correlation better? Feel free to pause the video here. So a few things that we'll be able to do is we could just understand how land cover has an effect on climate change, which would in turn allow us to maybe design more effective policy. For example, limit, settlement sprawl, control the type of materials, building materials being used in new cities and towns, maybe opt for lighter colored building materials that will reflect more of the incoming sunlight so that we don't create an urban heating effect. Also, we can just better understand and seek to maintain the balance of the potential feedback loops that exist on a regional and global scale that can be affected by changes in albedo of surfaces. If we're aware of that, we might be able to better avoid some sort of dip into a negative, a potential positive feedback loop that can have serious negative consequences for the Earth, one of which we'll be talking about in a moment. So why do we care about the effect of land cover and albedo and in turn climate? Go ahead and pause the video here and think about that for a moment. So we care about it largely because of the correlation between albedo and climate change. So the uneven heating of the Earth and the atmosphere is what drives weather over long periods of time, or drives weather over shorter periods of time and climate over longer periods of time. So this system has been perturbed lately, meaning it's been thrown out of balance. And what do you guys think is a major cause of this disturbance in the Earth's energy balance at this time? Well, the most significant one is probably climate change. So climate change acts through many different forces. A major one is the greenhouse gas effect, which traps more heat and energy in the Earth's atmosphere than would naturally be done or naturally be occurring in the Earth, creating an insulation layer which heats up the Earth past its natural range. Albedo is another force by which climate change can act. So albedo is a natural phenomenon, but when human activities cause it to be thrown out of balance, it can kind of set off a positive feedback loop in combination with climate change, which can have very significant and dangerous consequences. So what are some consequences of climate change that you guys have noticed we as a species are already experiencing across the world? Feel free to pause the video here and think of some. So there's many different things that we are experiencing due to climate change, but a few important ones are maybe more frequent and severe extreme weather events, such as hurricanes, fires like those in California, and floods. There's also drought and food shortages, increased disease range, longer pest life, air pollution and other health threats, less available clean drinking water. And then one of the very important ones is also rising sea levels and melting ice glaciers. So let's discuss this example of sea level rise / glacial and Arctic ice melting. What is causing these sea levels to rise? I suppose we just said that. It's mainly the melting of the ice, right? So Earth is warming up due to the greenhouse gas effect. Therefore, more sea ice is melting, causing sea levels to rise. This is the basic cycle as it exists right now. However, there are additional factors which can speed up or magnify this process, one of which is albedo. So once this process of sea ice melting begins, the effects of albedo cause a positive feedback loop to ensue. So which do you guys think has a higher albedo? Which is more reflective, ice or water? Ice has a higher albedo. It reflects more of the incoming sun rays. So meaning that is as ice melts into water, more of the sun's rays and energy are being absorbed at the poles, leading to further warming of the water and air around it, which causes more ice to melt, and the cycle goes on. So we can see in this image at the bottom here that sun that hits ice, about 90% of it is reflected, only 10% is absorbed. Whereas sun that reaches dark water, almost 94, like almost all of it, 94% is absorbed and only 6% is reflected. So if this ice is slowly receding and turning into water, more and more of the sun's rays are going to be absorbed, which heats up this water, which melts more of this ice. And so that's the positive feedback loop that ensues, and it just speeds up this process exponentially to the point where we will be losing glaciers much faster than we would if it was just if this albedo phenomenon was not contributing to the speeding up of the process. So I think this image is a really good one to understand a bit further what we're talking about. Ooh. So this is Greenland, and we can see it's kind of been split up into its components, that kind of the main ones that make up this landmass. So there's soil on the bottom, and then there's the glacial ice sheet, and then there's the water surrounding it. So the albedo of each of these surfaces is denoted here. So the soil surface albedo is 60%, meaning, or sorry, 40%. So 60% is absorbed, 40% is reflected. The albedo of the snow is 90%, so 90% is reflected and only 10 is absorbed, so a lot more is reflected. And then the albedo of the water is very, very low. It's only 10, so only 10% is reflected, while 90 is being absorbed. So we can see these range quite significantly. And it used to be that Greenland was almost all covered by this glacial sheet, but it's been receding lately, which exposes more and more of this outer dark soil, meaning that it heats up more, which again melts the glacial ice faster. So down here, we can see a really interesting graph that shows Greenland ice sheet albedo over the last, well, this is from 2000 to 2010. And we can see that the percentage, the albedo percentage has gone steadily and fairly quickly downwards. So it used to be that as a landmass, its overall albedo was about in about 80% or a little higher, 82%, meaning that 82% of the sunlight that hit it was reflected back out, and only the remainder, 18% or so, was absorbed. But this value has been going down steadily, meaning that less and less of the light is reflected and more is absorbed, to the degree that by 2010, there was already an area of ice the size of France which had melted. So we've discussed some goals of albedo research, but you might be thinking, Wisconsin Energy Institute, how does that relate to albedo? How does biofuels like ethanol, how do biofuels like ethanol relate to albedo? So this very topic is being researched, in fact, by a GLBRC doctoral candidate, Cheyenne Liu at MSU, Michigan State University. The aim of her study is to learn more about the role of albedo across different biofuel cropping systems. She wants to better understand how albedo changes between bare ground, peak growing, and harvest seasons, with the ultimate goal of assessing the global warming potentials of each biofuel cropping system. So here's a little image of the plot of land that she's using for her research, and it has lots of different squares that have different types of plants, biofuel crops planted on them at different stages of growth. Some of them don't have anything planted in them, and they're assessing how each of these plots of land exhibit a different albedo. and what that means for their global warming potentials. So the study is set up in Michigan at the Kellogg Biological Station. Towers were installed throughout this sort of field in different areas, and they were equipped with tools to measure incoming and outgoing short and long wave radiation, or the sun's rays, a camera to capture changes in vegetation, and tools to measure soil moisture. They were set up in many different fields with a variety of growing regimes to measure these features that we talked about. So here is a key at the bottom, which shows you sort of what the different planting regimes of these different plots are. Different plants, different stages of growing. Some of them are just laying bare in between growing regimes. Yeah. So some of the different biofuel plants that are used in these different plots include corn, sorghum, switchgrass, miscanthus, and native grasses. So the main goal of this study was to measure the albedos of these different plots over time and use methods which allowed them to scale up the information. So they were just looking at each of these kind of squares of plot on their own, but we're interested, of course, in being able to use this information and look at it on a grander scale. Of an entire field, for example, several acres covered in corn. What would that albedo be? What would the effect of that albedo be on warming? So the results of their study can inform our choice of biofuel crops. Out of all these different ones, which one do we choose? Of course, there are other things that go into it too, but the albedo of these crops is a very important kind of aspect of them to think about when we're deciding which ones we want to plant on a grand scale. Perhaps we will lean towards those with a higher albedo, meaning they reflect more light. So this may all seem kind of scary. Albedo is certainly speeding up climate change, as we discussed, but how can we stop glaciers from melting? That seems like a really big task, right? But there are a few positive things that we can use our knowledge of albedo to do. So feel free to pause the video here and maybe take note or think of some different things that you guys might see as practical applications of our knowledge of albedo. So a few important ones include maybe reducing expansion. So suburban sprawl is changing the albedo of maybe previously natural lands very significantly. And so if we can reduce that sprawl or be more conscientious about our use of land space, that's very important. Design smarter cities, better building materials. For example, like this image shows on the right side, there's a rooftop with a much lighter color than on the left, and it is cooler in that it reflects a lot more of the incoming sunlight and absorbs less than the roof on the left side, meaning that we have to use less power and energy in the right side of this building in order to keep it cool, because the outer materials of the building are already doing part of that job for us in reflecting some of those incoming sun rays back. So we can also make deliberate land use choices just across the board, protect natural grasslands, which, as we can see in the results of the Northern China study, natural grasslands have a higher albedo than agricultural fields, which are often what natural grasslands are turned into. So it's important to see that when we're converting natural grasslands into agricultural fields, we're often decreasing the albedo a bit, meaning more light is absorbed and less is reflected, which can lead to a heating effect. So, but above all, the maybe most significant thing that we need to all be working at is addressing climate change. So again, that's difficult as an individual, but we all have to do our part to try and decrease our carbon footprints. And when you're able to, vote for leaders who want to do the same on a bigger scale. So thank you guys so much for tuning in to this recording. If you guys have any questions, feel free to email me. My email here is the second one, alanarapp, wisc.edu. Yeah, feel free to email me with any questions you guys might have had during this presentation, and I'll do my best to get back to you. Also, there's more contact information here listed of my other colleagues, and then the Wisconsin Energy Institute website and the GLBRC website as well. So thanks so much for tuning in, and hope you guys enjoyed the lesson and learned something new about albedo.